Section 3.6 is the last section in Chapter 3 that we're going to cover in our class, which I know, yes, is sad. Chapter 3 is coming to a close, but I have good news for you, and that's that every problem in this section is a word problem, and I know that they're your favorites, so no need to thank me. But this section we're talking about related rates. And this sort of takes everything we've talked about in Chapter 3 and ties it up together in a way that really makes a lot of quote-unquote real-world sense. Every single problem that we look at here has some sort of real-world application. So I think it's a really cool section, and I think it's a pretty important one too. So we're going to look at this first example here, and I'm going to walk you through the process of looking at a related rates problem, because some of these can be kind of tricky. These word problems, there's just a lot going on in them, so I'm going to kind of describe the steps that we might want to take when we're trying to solve these. We're going to look at a classic example. Here we have the ladder problem. It says a 26-foot ladder is placed against a wall. If the top of the ladder is sliding down the wall at 2 feet per second, at what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? So step 1 and step 2 I sort of almost grouped together. In step 1, if it's helpful, draw a picture. And I think a lot of us would have probably guessed this. But step 1, draw a picture if it's helpful. In step 2, I'm also going to throw that in as well. It says identify all relevant variables, blah, blah, blah. I'm just going to say, let's call that organize your information. Organize your information. And if it's possible, use your picture to help you organize your information. So I have a 26-foot ladder. So here's my ladder leaning up against a wall. And I'm also going to give these variable names here. So I see, here's the ladder if you need to see what's going on here. I've got a right triangle. That will be useful information for us later. Right triangle makes me think of a squared plus b squared equals c squared. So how about we call this side A, we'll call this side B, and then the hypotenuse we'll call C. So let's see, what do we know? We know that the ladder is 26 feet long. So the hypotenuse, that's the ladder, C is equal to 26. It says if the top of the ladder is sliding down the wall at 2 feet per second. I'm going to come back to this 2 feet per second here in just a little bit. I want to cover some other stuff first, because this is the way we handle this is just a little bit different. We want to know at what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet from the wall. So the bottom of the ladder, B, that's 10 feet from the wall, okay? And I don't know A, but we could figure that out just using Pythagorean Theorem, right? I just said earlier, I've got a right triangle, makes me think about a squared plus b squared equals c squared. Let's go and find A really quickly. If I have a squared plus b squared, that's going to be 10 squared is equal to c squared, that's 26 squared. So I have a squared plus 100 is equal to 676, which means a squared is 576. Oops, 576. And let me just double check my mental math, but I believe we end up with 24 here. I take square root of 576, yep, I end up with A is equal to 24. So I've got all of the sides of my right triangle, all of the sides of my drawing labeled here, which is a good start. I think that's a good start in organizing your information. But I said, hey, let's come back to this 2 feet per second now, because in every single one of these problems, the section name is related rates, and I'm going to highlight this word rates here. That's what I really want to draw your attention to, because we're talking about rates of change. And hopefully when I say that word rates of change, your mind jumps to derivatives, right? Because the derivative tells us the rate of change. So I also like to kind of draw in some arrows so that I know what's going on. It says if the top of the ladder is sliding down the wall. So here's what's going on. The top of the ladder is sliding down the wall. It's going down. Think about what's going to happen then. The bottom of the ladder right here is going to get kicked out in that direction. It's going to move to the right here. So it says if the top of the ladder is sliding down the wall at 2 feet per second. So that's telling me the rate of change of this side. It's sliding down the wall. So that's the rate of change of A. Now, this is the rate of change of A, so I'm going to call this dA. So this is the rate of change of A with respect to time. And you might say, well, how do you know it's time? Well, look at your unit. Look at your unit here. Feet per second, right? Feet per second is our unit. So that means that's dA over dt. And now, okay, if I say this is the rate of change of side A, you would tell me, okay, well, that's going to be 2. You would be almost right if you said 2, but not quite. You're missing one little teeny tiny thing here. Think about what's happening to this side of my triangle. Is this side of my triangle getting longer, or is this side of my triangle getting shorter? As time moves on, it should be getting shorter, right? As time moves on, we might have something that looks more like this, in which we might say, okay, well, this side, right, is shorter than this side. Or excuse me, that side is longer than that side. The new triangle that I have has a shorter side. So in other words, the length of that side is decreasing, which means that the derivative should be negative. I know not all of us are really big fans of this notation. I think it's probably the clearest way to write it, but if you really want to, we could also use A prime for that as well. So we could say either A prime or dA over dt is equal to -2. Let's see, what else? Because I want to talk about the derivatives of all of these sides. I'd like to be able to talk about, well, what is dc over dt, and what is db over dt? Let's see. What else does the problem tell us? Let's maybe erase some of this so that we can look. We've talked about the 26 feet. We've talked about the top of the ladder sliding down. It says, at what rate is the bottom of the ladder moving away from the wall? That's describing this rate of change, the rate of change of side B, which means that dB over dt, that's what I'm looking for. So at the end of this problem, I would like to be able to say dB dt is equal to this, whatever that number is. dC dt, this one's a little bit tricky. What is this? This is my ladder. So here, that's my ladder. dC dt, think about, is this side getting longer or is this side getting shorter? Well, it's a trick question, actually, because it's not getting longer and it's not getting shorter, right? It's neither one. If it's not getting longer and it's not getting shorter, the rate of change must be 0. So that means dC dt, or C prime, must be 0. So at this point, I've kind of laid out everything that I know, and I've identified exactly what I'm trying to find. And actually, I kind of skipped ahead. This is your step 3. Step 3 is to express all rates as derivatives. Express all rates as derivatives. So here we're using either A prime or dA over dt and so on for each side of my triangle. So okay, these 3 steps together I think are the hardest steps of these problems, but they're also the most important. A lot of the difficulty of this problem just comes from digesting all of the information that this problem is giving you and organizing it in a way that makes sense. So if you look at the picture that I've drawn over here, I think we've done a really nice job of organizing that work and organizing that information. I can look at each side of my triangle and I can find exactly what I'm looking for. So honestly, I think sort of half the battle is just organizing your information in a way that's easy to understand. Step 4, okay, here's here's some new stuff. I need to find an equation that relates all variables. So this does not necessarily need to relate the derivatives. So we don't need to relate dA over dt or dc over dt. Those are all going to come later. I just want to relate A and B and C. I need some relationship between those three variables. And actually, we've already used the one that I have in mind. If I have a right triangle, I have the sides. I'm thinking about a squared plus b squared equals c squared. So that is the equation that comes to mind for me. I'm thinking about a squared plus b squared is equal to c squared. Sometimes this equation will be given to you. Sometimes you'll have to come up with it on your own. But here we've got our equation that relates those three variables. That's great. So now in step 5, here's where our derivatives are going to come into play. We want to implicitly differentiate your equation with respect to t. And then in parentheses, I'm going to write chain rule here. Because remember, implicit differentiation, we said, was sort of just an extension of the chain rule. So the chain rule is really, really important here. So I want to take the derivative of each side with respect to t. So I want to look at the derivative with respect to t. Again, we don't use this notation all that often, but I think it's helpful here. A squared plus b squared equals the derivative with respect to t, c squared. So I'm going to take the derivative of each one of these with respect to time t. So the derivative of a squared would be 2a times, for my chain rule, I need to multiply by the derivative of a with respect to t. So dA over dt, because this side a is changing over time. This side over here is changing over time. So 2a times dA over dt plus 2b times dB over dt. So I'm just taking the derivative of b squared. That's how I come up with 2b times dB over dt. There's my chain rule. The right-hand side, same idea. Derivative of c squared, we would say, okay, well, that is 2c. Applying our chain rule, we're going to have times dc over dt. So that was my step 5. Step 6, our last step here, we want to solve for the missing rate. And here we should just have a little bit of substitution, a little bit of algebra to do here, because we have this relationship now that relates A and dA dt and B and dB dt and C and dC dt. And if you organize your information well, and this is why I think this step is so critical, look at this. All of our information is very clearly laid out right there. So I just need to take A equals 24, plug that in. C equals 26. dA dt equals negative. I have all of this information. I'm just going to plug it into my derivative. So let's do that here. So 2 times A, we said A was 24. So 2 times 24 times dA over dt, that is negative 2, plus 2 times B, times B, what is B? Well, B is 10. So 2 times 10 times dB dt. Now, notice we don't know what dB over dt is. But that's okay. That's what we're trying to find. So I'm going to leave that as dB over dt equals, on that right-hand side, 2 times c. C is 26 times dc dt. What did we say that was? We said that was 0 because that side is our ladder. It's not getting longer or shorter. So times 0. And now I have this equation that I can solve for dB dt. So I'm just going to go ahead and do a little bit of algebra here. So let's see, I should have negative 96, for my first term, plus 20 dB over dt equals 2 times 26 times 0. I'll have 0. So again, I'm just trying to solve for dB dt. I'm just treating it like I would a variable here. I'm going to add 96 over, so 20 dB over dt equals 96, which means that dB over dt equals 96 over 20, which, if we wanted a decimal approximation, I believe 4.8. Yes, 4.8. There's two things I want to check at the end. First, I would recommend that you check the sign of your answer. So here we have a positive 4.8. And just ask yourself, does that make sense for our problem? Because sometimes a positive answer might not make sense. Go back and look at what's happening in the problem here. We said that B, this side right here, is getting longer. Does it make sense then, if that side is getting longer, that we have a positive rate of change? Yes, I think so. If that side is getting longer, right? If B is getting bigger over time, that means that dB dt must be a positive number. So it makes sense that we have 4.8. The other thing I would like you to give with your answers is a unit. So 4.8 what? And to tell the unit, I would look at your derivative over here, and this is why, another reason I think this notation is helpful. dB dt, so just look at dB here. What are the units on B? B was a side length. We measured that in feet. So 4.8 feet per dt, and we're talking about time. My unit of time was seconds. So I have 4.8 feet per second is my dB dt. So there's a lot going on here. I think this is kind of a more complicated example, but it does a really nice job of kind of showing you all of the steps that you need to take. Some of the problems that we look at, yes, will be a little bit simpler than this. Some might be a little bit more complicated than this, but this example does a really nice job of illustrating all of the steps that we're going to have to take when we're solving a related rates problem.